practicing in each and every one of the assignments. After we put together the data, we have a good understanding of the data, so we can't just blindly plug in the data to the algorithm and run without knowing what the data is, obviously. We have to have a very good understanding of the data that we are using, and there are some tools to do that, doing visualization, graphs, bar charts, you've seen all of that stuff. It's fun. Then we choose different algorithms appropriate to the task, and we run experiments, produce predictions, we do validation, we do training, validation, and testing, and then we measure the accuracy, we produce the measurements and the reports. And then another very important step is error analysis. So in the areas that the machine is making a mistake is of vital value in terms of insights, because those are the weaknesses that maybe would provide us with some clues to go back and reorganize the data or add some more variety of data to rectify that weakness. But it may not be a weakness, it may be some logical reasons behind. So the source of errors are usually a source of extremely valuable insights. It's a very important step. It's called error analysis. Basically, we look at the areas of the data that the machine made a mistake, and then we analyze those areas and report. The storytelling and visualization is, again, very iterative. We did it as part of the data preparation, but at the end, we also do extensive visualization to help us communicate the result. Like I said, the communication is of extreme importance, and the more effective we can communicate, the better. It doesn't have to be experts on the audience. It has to be communicated, especially for everybody to get an understanding of what was the business formulation, what did we do, how we did it, and more importantly, what is then how. Although most users are very curious to know how we did it, but the priority is to communicate what it was that we did, what it is that we produce, what is the meaning of the result. So the interpretation of the result is also extremely important. So another important, that I mentioned, is the distinction between how and what. When we communicate, is mostly concentration on the what, let alone the fact that how the model is doing is also mostly a black box. But it's I always have a challenge to say to my executives, leave the how with me. You tell me what it is that you need. This is an example of a visualization. I have a hard time convincing them, but that's another point. In this visualization, you see on the right side, we see the distribution of the deliveries overlaid by the out for delivery. So when the item goes out of the depot as a distribution of time, so the letter carrier or the delivery agent goes out the depot with the packages, that has some time distribution. And also when it's in the neighborhood, there is another distribution showed by red. That is the distribution of the actual final delivery time. So you see the overlay of the two distributions have a different peak. And also the blue one, the out for delivery, has two peaks, meaning that the delivery agent maybe goes out twice with a large volume during the day. And obviously the x-axis is the time of day. So on the left, you see that, on the amber, we have segmented different neighborhood types. and the one that is green has a more well-behaved distribution of the delivery, and it's more predictive, if you will. And the one at the bottom with red has more sporadic distribution of delivery. So we communicate this through this visualization so that the user understands the difference between these principal segmentations of the routes and the neighborhoods. Again, when you have a very effective and easy to digest visualization, it's extremely helpful to make the message come across. So capitalize on that. Highly recommended. Also, parallel to those segments on the left, the pie charts are showing the volume associated with those segments. So the combination of the two, you on this page, you have a one-pager with these three different charts, and the fact that they are together give a good insight of what is going on the delivery side. That's what I meant by understanding the data. This is not involving any model output or prediction or anything. It's purely the facts. This is the visualization of the data that we were going to use for time prediction. These are the type of activities that you are expected to do as part of your assignments. Another perspective of data visualization, in this case, you see if we were to predict the time of delivery, where the fact of the dots or delivery, and you have a window band of the averages of the deliveries, you see those outliers that are either delivered very late or early in the morning are going to be harder to predict. What does this say to me is that if I took the average as the prediction, I have a 92% accuracy because of those late and too early items that are kind of sporadic deliveries without any modeling. Again, this is a purely average calculation and looking at the data. So when I do the prediction, this could be a baseline. If I have 92%, if I only told the average, then when I do the modeling, I invest in the exercise of the modeling, it has to beat the 92% average. If it is more accurate than that, then it would be worthwhile. Otherwise, I just go with the, in the absence of any modeling. Again, going back to the comment I made earlier, it's fancy tools to use because of fanciness. No, it has to be, there should be a reason to use the tool to serve a purpose. So high-level perspective is important. Another visualization, the overlay of the prediction and the reality. You see the red dots are the model predictions, and it has hard time predicting the outliers that are exceptionally late or early. For whatever reason, those days, the delivery agent had a coffee, or it was slippery, or force majeure, or bad weather, or whatever reason that the delivery happened in an abnormal fashion. And that's the exception that is harder for the machine to predict based on the historical data. So the bias that some of you were commenting, when my historical data falling mostly within the bandwidth of the window that you see on the average, then my model is biased towards that average because larger volume of the training data is, skewing towards that. So then it has harder time, but it's just, we have to be cognizant of the bias. Maybe this is not a good example of the bias, but the variability and the bias are the trade of two extreme of the same spectrum that we have to be very conscious of. That ties in with the nature of the historical data. Another reason to be aware of the nature of the data that we are using, because you get what you feed to the model. So, like I said earlier, we have to measure the performance, and there are different techniques to come up with a fair argument regarding the measurement of the accuracy. One of the common practice in evaluation of the model is that instead of taking a 10% random once, we do that 10 times. So this is called tenfold cross-validation. If you see on the right side, we divide the data into those folds, and then we use different segments of the data as training and different segments as test each time, and then we take an average of the accuracy of the 10 times training and testing. And then that would be more confident to report the accuracy as opposed to doing only once. You see this, the reason behind it, right? So we stratify the data, and then we do the test and training 10 times with different folds, so that if there is any bias, you reduce it if any segments of the data produce any bias, increasing the variability. This is an example of the reports on the validations. On the right side, you see the bottom right, validations and training in different segments of the data. And on the top left, you see the overlay of the training and validation curves, again, in different percentiles of the data. And on the right, it's the fit statistics showing a lot of evaluation indices for that are common practice in regression. So in this case, the target variable is continuous. Another thing that we need to be cognizant of is the type of the variable. The variable could be nominal or discrete, or it could be continuous. An example of a continuous target variable is time. Time is a continuous variable. But a binary target, such as a sentiment, is a yes and no, and it would be a discrete variable example. Or if I want to predict the days of the week, which day it's going to be, would be another nominal target variable that has 7 values, days of the week. Another very important example of a confusion matrix that based on which we produce, there are important indices in terms of evaluation. You see on the top left, the accuracy, precision, and recall. They have different definitions that all derived from the table on the left. It's a confusion matrix. You have the predictions versus the actuals. So if you have a binary yes and no target, it could be, let's say in the left, you have the actuals, and then on the top, you have the predictions. So there are 4 possibilities. It could be that the no, the model also picked the no correctly, or it could be the yes that also model picked yes. But then it could be a no that the model said yes, and it could be a yes that model said no. So these are all forming the definitions of precision and recall that you need to get familiar with. It's important how we dissect the predictions in the discrete situation to show the proxy on the confusion matrix to get a sense of how the result looks like. Again, these two gray ones are the same numbers, showed in a different way based on the calculations that, we can do using these 4 quadrants of a confusion matrix in case of a binary. If the values were more than 2, then your confusion matrix would be bigger, obviously, because you have more permutations, combinations of the predictions and the actuals versus the actuals. We will review all of that in the coming sessions. It's just today I want to give you an overall perspective of what is involved in the course, because I want you to have a long preview of the whole thing so that it would reduce your nervousness about the course and you are more aware of what is the expectation and the material that you need to focus on and learn. This is another example of the application of the machine learning in the context of unstructured data. In this case, the formulation is that we want to classify the poems based on the era or the lifetime of the poet. We have 5 different labels, young, mid-age, and old, and 2 in between of these 3 main segments of the lifetime of a person. And the objective is to put any poem in the machine, and machine would tell whether this was made when the poet was young or old. So that's the formulation of the problem. And then we went to trying different representation of the data, and we use different machine learning algorithms, and then we look at where the machine was wrong, and we try to get an intuition what was the reason behind those mistakes, so that it would help us understand the nature of the data. So you appreciate, I hope, the fact that there are very diverse context on the machine learning applications, and you would feel free to choose your own final in any context that you are interested in. Sky is the limit. This one was in digital humanities. Another more detailed perspective of the steps involved in machine learning activities, that on the left side we take the data, we do different representation transformation on the data. Important ones are bag of word and TF-IDF, and then we use the model latent Dirichlet allocation, LDA transformation, and then we use the SVM machine learning algorithm to do the predictions of the poems. So these are the important transformations that we will learn in the coming next class and the following, when we are going to look at the classification, so that you would be prepared to do your assignment 1, which will be posted very soon. This is an example of the communicating the results. So as part of the evaluation exercise, we did on the left column a variety of different representation transformation on the data, and we used SVM, and you see every row correspond with that representation accuracy of the model. For example, the LDA similarity at the bottom, 70 or 80%, 79.5% accuracy was achieved, which was much higher than the other representations such as bag of word and an LDA. So these are the 4 columns are important measures that we report because each has a different meaning and altogether give a better understanding of the behavior of the model: accuracy, precision, recall, and F-score. These are the ones that, there are so many others, but these are the ones that you're expected to know by heart as part of this course. Okay, take a couple of minutes break and we change gear on a different topic, a little bit of a different topic. I also answer any questions you may have. Who is Hafez? Google it, my friend.